In early 1943, German radar operators believed they had mastered the night sky. Their scopes glowed with confidence as bomber streams appeared exactly where doctrine said they would. Every sweep of the cathode ray tube confirmed what the Reich had spent years building, an invisible wall of detection stretching across Europe. In concrete bunkers along the coast and deep inland, young technicians tracked glowing blips with near-religious faith. The system worked. It had worked all through 1942. And because it had worked, no one seriously imagined a night when it wouldn't. That confidence was born from hard numbers. RAF Bomber Command had paid dearly the year before. Loss rates climbed toward levels that quietly alarmed even Britain's most determined planners. Aircraft disappeared into the darkness and never returned. Crews learned that the Germans did not need daylight to kill them. The reason was the Kammhuber line, a layered defense built on Freya early warning radar, feeding Würzburg fire control sets. Freya saw the intruders coming. Würzburg pinned them in space. Night fighters and flak batteries were then guided with mechanical precision. It was not chaos, it was choreography. To German commanders, this integration was proof of permanence. Radar was science. Science did not bluff. As long as operators followed procedure, the sky would remain legible. When contacts appeared, intercepts followed. When intercepts followed, bombers burned. The enemy might build more aircraft, but they could not escape mathematics. Then the reports began to change. In the weeks leading into the Hamburg operation, radar stations started logging anomalies. Screens filled faster than expected. Targets overlapped in ways that defied established patterns. Controllers initially dismissed it as weather. Atmospheric disturbance was a familiar enemy, and the North Sea was rarely cooperative. Others blamed calibration drift or tired operators. No one suggested deception. The system was too refined to be fooled so easily. On the critical nights, nothing about the bombers themselves appeared different. Altitudes were familiar, speeds were unchanged, formations followed known approaches. Yet, as the bomber streams crossed into German airspace, radar displays no longer told a coherent story. Where there should have been dozens of aircraft, there were hundreds, then thousands. The scopes dissolved into shimmering noise, like snow on a dead radio signal. Commands hesitated. Fighters were launched late, or not at all. Flak fired blindly, guided more by instinct than data. Inside the bunkers, tension replaced certainty. Operators double-checked dials. Supervisors demanded explanations no one could give. The system that had promised clarity delivered confusion instead, and confusion spread faster than any bomber stream. By the time Hamburg burned, German commanders knew something fundamental had failed. They blamed weather, sabotage, even operator error. None of it explained why. Every radar in range failed at the same time. Somewhere far from the bombers, a single engineer had already changed the rules of the war. German radar was brilliant, precise, powerful, and engineered to near perfection. It was the kind of system that reflected the nation that built it. Methodical, exacting, confident in rules and measurements, each component of the air defense network was designed to do one thing extraordinarily well. And for a time that philosophy paid off. Night after night, radar guided fighters and guns with lethal efficiency. Yet hidden inside that success was a flaw so fundamental that few inside Germany ever questioned it. Precision, taken too far, can become a trap. At the heart of the system was the Würzburg radar, operating around a tightly controlled frequency near 560 MHz. Its narrow bandwidth gave German controllers remarkable accuracy. They could track a single bomber, assign a fighter, and guide an intercept with confidence measured in meters. But such accuracy came at a cost. The system assumed the sky would behave honestly. It assumed that reflections meant aircraft and that echoes could be trusted. Flexibility was sacrificed for clarity, and no one imagined an enemy could turn that clarity against itself. Across the channel, Allied intelligence was slowly assembling a very different picture. Captured radar sets, wreckage from downed aircraft, and careful signals analysis began revealing how German radar actually saw the world. Frequencies were mapped. Pulse patterns were measured. What emerged was not mystery, but predictability. The German system was not adaptive. It did not ask questions. It simply processed returns and displayed them as truth. Inside the British Telecommunications Research Establishment, scientists began to recognize the opportunity buried in that rigidity. If radar worked by interpreting reflected energy, then the battlefield was no longer just aircraft and guns. It was mathematics, and mathematics could be manipulated. The challenge was not whether German radar could be fooled, but how to do it at scale. The solution could not involve new aircraft or complex equipment. Bomber Command needed something crews could use immediately, under combat conditions, without training or modification. It had to be cheap because it would be expended by the ton, and it had to be fast because every night without it meant more crews lost to a system that seemed unbeatable. The radar problem was brutally simple. Würzburg could track only so many targets at once. If the number of echoes multiplied beyond that limit, the logic collapsed. Controllers could not tell real aircraft from false ones. The strength of the signal no longer mattered. The display would drown in its own information. What the scientists had, at this point, was theory, elegant, convincing, and useless on its own. Bombers could not survive on equations. To turn insight into protection, they needed a physical answer, something that could be built by the millions and dropped into the sky like seeds. British scientists had the theory, but theory wouldn't save bombers. What they needed was a physical object so simple it would look like trash. And that object would be perfected, not by a general, but by an American engineer. It didn't look like a weapon. It wasn't forged steel, secret circuitry, or a machine that roared to life. It was thin, reflective, and light enough to drift on air currents. When the idea was first placed on a table in front of senior officers, it drew polite smiles and quiet disbelief. This, they were told, could save bomber crews. To men accustomed to thinking in engines and explosives, it sounded absurd. The concept came from an American physicist working alongside Allied radar countermeasure teams, a man more comfortable with equations than ceremony. While others focused on overpowering German radar with stronger signals, he asked a simpler question. What did radar actually respond to? The answer was reflection. A radar pulse left the transmitter, struck an object of the right size, and returned home as proof that something was there. If that was true, then an aircraft was not the only thing capable of talking back to radar. The breakthrough came with wavelength math. German Würzburg radar operated on a known frequency. If a piece of metal was cut to exactly half that wavelength, it would reflect radar energy with surprising efficiency. Not scatter, not weaken, reflect. In laboratory tests, thin strips of aluminum behaved like perfect radar mirrors. One strip looked insignificant. Thousands of them looked like an armada. The materials were almost insulting in their simplicity. Aluminum foil, bonded to paper or fine string, cut by hand into precise lengths. No rare metals, no skilled labor. A small bundle could be assembled quickly and cheaply. The cost worked out to roughly $2 per bundle, a trivial sum compared to the price of a bomber or the life of a trained crewman. The British called it window. The Americans, with characteristic bluntness, would later call it chaff. Each strip was tailored to the German radar frequency, matched with scientific care. When released from an aircraft, the bundles would separate and spread, drifting slowly through the air. To radar, they did not look like debris. They looked like aircraft, thousands of them. Each bomber could carry enough to create an entire phantom force, and crews could deploy it simply by pushing it out of the aircraft by hand. No aircraft modification was required, no new training. It fit seamlessly into operations. What made the idea unsettling was not its complexity, but its openness. There was nothing secret about aluminum foil. If it worked, the Germans would understand it almost immediately. They could copy it just as easily and cheaply. That reality terrified planners. For years, both sides had avoided using such countermeasures, not because they didn't know about them, but because they feared losing the advantage of surprise. Now the pressure was unbearable. Bomber losses mounted. Crews demanded protection. The $2 solution waited, humble and unassuming, for a decision far larger than itself. The idea was devastatingly simple, but there was a terrifying catch. If the Allies used it first, the Germans could copy it within days. The decision to deploy would risk everything. On the night of July 24, 1943, Allied bombers crossed the German coast exactly as expected. Routes, altitudes, and timing all matched familiar patterns. In radar bunkers from the North Sea inward, operators settled into routine. Screens bloomed, with returns steady and readable. For a moment, it appeared that nothing had changed. Then, almost instantly, order collapsed. The displays filled with contacts that made no sense. Where there should have been organized streams, there were impossible numbers of aircraft appearing at once, overlapping and multiplying beyond logic. Operation Gomorrah had begun, and with it came the first mass deployment of Window. As bombers approached Hamburg, crews quietly released bundles of aluminum strips into the night air. They drifted, spread, and lingered. On German radar screens, the effect was catastrophic. Würzburg's scopes, designed for precision, became useless. The tracking systems were saturated beyond interpretation. Controllers could not tell which echoes were real aircraft and which were ghosts. The sky, once neatly mapped, turned opaque. Inside command centers, confusion replaced authority. Night fighter controllers attempted to assign interceptions, but there were too many targets and no way to prioritize them. Fighters were sent toward clusters that dissolved before they arrived. Others chased echoes that never moved. Communication lines clogged with questions no one could answer. The radar picture, the foundation of the entire defense system, could no longer be trusted. On the ground, flak batteries faced the same blindness. Guns fired where doctrine said bombers should be, not where they actually were. Ammunition burned into the night sky with little guidance, while operators strained to reconcile what they saw with what the instruments told them. For the first time since the system was built, German air defense was reacting instead of controlling. The difference in outcome was immediate. Bomber losses that had once been accepted as the price of doing business dropped sharply compared to earlier raids. Crews returned reporting something unheard of. They had passed through German airspace with less opposition than expected. Not because the defenses were absent, but because they were paralyzed. German after-action reports struggled to describe what had happened. The phrase radar fog began to appear, an attempt to name a phenomenon that defied training and experience. No equipment failure could be identified. The radars were working exactly as designed. That increasingly seemed to be the problem. As fires spread through Hamburg, civil defense systems were overwhelmed. Bombing accuracy increased, not because the bombers were better, but because the defenses meant to disrupt them had lost coherence. The Kamm-Huber line, once a symbol of control, revealed itself as brittle under pressure. Within hours, German high command understood the truth. Their greatest defensive advantage had been neutralized, not by a new bomber or fighter, but by something they could have built themselves. German planners believed technological superiority meant permanence. Their radar network had been built with care, tested in combat, and refined over years. In their thinking, once a system achieved dominance, it stayed dominant until replaced by something more advanced. What they underestimated was not Allied science, but Allied character, especially the American instinct to improvise, simplify, and then scale an idea until it reshaped the battlefield. The German response came quickly, at least on paper. Engineers understood what had happened almost as soon as window was used. They developed their own versions of radar reflective strips and began testing countermeasures designed to filter out false echoes. But understanding a problem is not the same as solving it under fire. German industry was already strained, and adapting complex radar systems took time they no longer had. Across the Atlantic and in Britain, the reaction was entirely different. Allied factories did not debate whether chaff was elegant or dignified. They asked how many could be made and how fast. Production lines were adjusted, paper and aluminum allocated, and within weeks, output reached into the millions of bundles per month. Chaff was no longer an experiment. It became routine, packed alongside bombs and fuel, issued as casually as maps. This was logistics as a weapon. The power of chaff was not just in its design, but in its abundance. Every major raid carried enough to overwhelm defenses again and again. German radar operators never knew if tonight would be another night of blindness, and that uncertainty eroded confidence. Countermeasures designed to distinguish real aircraft from reflections lagged months behind deployment. Each fix arrived too late and worked only briefly before being overwhelmed by sheer volume. As 1943 wore on, the effects became undeniable. Night fighter effectiveness collapsed. Pilots found themselves chasing phantoms or relying on visual sightings in darkness, a method far less effective and far more uncertain. Radar crews, once calm and authoritative, now worked under constant doubt. Screens could no longer be trusted, and decisions carried a sense of futility. The bombing campaigns reflected this shift. Attacks against German industrial cities accelerated, not because the Allies had suddenly become invulnerable, but because the defensive system meant to impose order had lost its edge. The psychological toll was profound. Men trained to believe in instruments were forced back onto intuition, and intuition failed in the dark. This was the true miscalculation. German leadership had assumed the Allies would play the same game, trading complexity for complexity. Instead, they faced an opponent willing to use something crude, cheap, and overwhelming. American improvisation, amplified by industrial scale, turned a clever idea into a permanent condition. By the time Germany adapted, the damage was irreversible, and inside Allied command rooms, a deeper realization began to form. This wasn't just a trick, it was a new way to fight. After the war, German officers were asked what had surprised them most. Many of the questioners expected answers about heavy bombers, tanks, or overwhelming manpower. Instead, again and again, the responses circled back to something almost embarrassing in its simplicity. Aluminum strips, falling slowly through the air. To men who had trusted instruments and equations, that memory lingered longer than explosions or engines. What they were describing was not just a technical defeat, but a philosophical one. Chaff did not disappear when the war ended. It became a permanent feature of modern warfare, woven into planning as naturally as fuel calculations or weather reports. In Korea, in Vietnam, and in later conflicts, aircraft continued to scatter reflective material into the sky, confusing sensors and buying time. The method evolved, but the principle remained unchanged. Radar could be deceived, not by brute force, but by understanding how it thought. The shock forced a shift in doctrine. radar designers learned that operating on a single frequency was an invitation to manipulation. New systems became multi-band, adaptive, and layered, constantly changing the way they searched the sky. Engineers began designing, not just for performance, but for resilience. The lesson was institutionalized across militaries. Complexity creates vulnerability when it is rigid. Precision without adaptability invites exploitation. Yet behind all of this stood a quiet legacy. The unnamed engineer and the $2 solution never fit neatly into heroic narratives. There was no dramatic unveiling, no parade of a revolutionary machine. What endured was the inversion of expectation. In the industrial abyss of total war, where nations measured strength in factories and tonnage, cheap mass defeated exquisite precision. Paper and foil reshaped strategy more effectively than steel. This was the moment of realization. Victory did not always belong to the side with the most advanced device, but to the side that understood systems as living things, capable of being confused, overloaded, and turned against themselves. It was a realization that reached far beyond radar rooms and bomber crews. It influenced how Americans approached problems in science, industry, and warfare in the decades that followed. The German radar network was not destroyed by force. It was rendered irrelevant by understanding. And in that quiet moment, when a screen filled with ghosts, the war entered a new era, where brains could outweigh steel and simplicity could dismantle empires. History only stays alive when it is remembered, questioned, and passed forward. If stories like this matter to you, stay with us as we uncover the quiet decisions and unseen minds that shape the world we live in today. And as you think about this moment, when simplicity defeated power, ask yourself this: how many turning points in history were decided not by force, but by someone who simply understood the system better than anyone else?